Hi everyone, I'm Gregorio and I'm a PhD student at Sapienza. I'm here to talk about a new paper that's part of the literature on learning theory applied to algorithmic game theory topics. In this case, we talk about profit maximization in bilateral trade, and for this problem, we show nearly tight regret bounds. This is joint work with Paul Duetting from Google, Federico Fusco from Sapienza, and Chris Schwiegelshohn from Aarhus University. So let's start, and we start by first defining what bilateral trade is. So bilateral trade is the prototypical two-sided market setting where two agents want to trade a certain good. Both agents have their own valuations about this good, and there is a self-interested intermediary that enables the trade. From a mechanism design perspective, what you want to do is to design a profit maximizing intermediating algorithm. So this is an algorithm that maximizes the profit of the intermediary. So let's start with a simple example, very simplified example. So let's say that the seller has valuation 100 and the buyer has valuation 120. Then both the agents report to the intermediary, the monitor, their actual valuations. What happens, and this is also very simplified, is that the monitor tells the buyer, look, you have to pay 120, and tells the seller, look, you are going to get 100. What happens then is that the buyer pays 120, the intermediary gets 20, and the seller gets 100. Here we're simplifying things a lot because, for example, the fact that the players actually report their valuations to the monitor is not a given. You need to enforce this from a game theoretical perspective. And also, the pricing functions will never be the identity. So it will not happen in general. It may happen, but it will not happen in general that the monitor is telling both the players to pay or be paid their actual valuations. Since we do learning, we do need to either learn over time or learn with a sample. In our case, we do learn over time, so our learning protocol is repeated bilateral trade. So at this time step, a new pair of seller and buyer arrives, and each of them has their own private valuation, which is in 0, 1, without loss of generality. It can be any compact set. And what happens is that the learner then posts a mechanism with allocation region, which is a subset of 0, 1 square, and two prices that map from 0, 1 square to 0, 1. These prices simply say are basically the prices that are asked to the buyer and that are paid to the seller. Then once the learner posts the mechanism, the agents declare their own valuation vector, and the trade happens if and only if the valuation vector belongs to the allocation region. And then payments are made accordingly based on the pricing functions that were attached to the mechanism. The learner is then awarded the resulting profit, which is just the difference between the price which is paid by the buyer and the price which is paid to the seller, conditioned on the trade happening. Since we do want to maximize profit, we need to be sure that we're actually doing this. So for us, the metric to understand whether we are doing good or not is regret. And the regret is taken with respect to the best mechanism in hindsight. So to be more formal, let's say that we have a learning algorithm A and a sequence of distributions and valuations S, which is what we can call the learning instance. For these two elements, we define the instance-dependent regret as the difference between the profit that we could get with the best mechanism in hindsight and the profit that we are actually getting by posting our sequence of mechanisms. And we are taking the sum over time since we want to understand what we are doing. So what's our performance over time? So the actual regret is then the supremum over the instance dependent regret. So we take the supremum over the whole set of sequences of distributions and valuations that we are considering. Now, we do want the regret to be sublinear in T because if it were linear, then what would happen is simply that we are not learning anything. because profit is a bounded function, so if regret has a linear rate of growing, then there is no learning happening because we are simply posting anything, and we are sure that posting anything, we are for sure getting a linear rate in regret. So as soon as we are obtaining something which is sublinear, we are definitely doing learning, and you would like to have learning as fast as possible. So we would like the regret to be sublinear at the best possible rate. Given the previous definitions of regret and learning instance, then we can model different online learning scenarios. So for example, in the adversarial setting, we have that the sequence of distributions S puts, so this sequence S puts all the mass, all the probability mass on single points. And in this case, we are playing against any specific fixed sequence decided in advance. This is stronger than a generic IID setting, and we cannot have sublinear regret in this case. We do prove it. So the hardness can be proved with Yau's minimax principle that relates the performance of deterministic mechanisms against randomized sequences with randomized algorithms against deterministic sequences, which is our specific target, let's say. Now, in the stochastic IID setting, where we draw the evaluation vector from a certain distribution at each time step independently, without any assumption on D, then in that case, we are able to prove a square root T regret. And this regret is tight up to polylogarithmic factors that appear inside the square root. I mean, you would have, for example, a log cube of t inside the square root, but apart from that, everything is tight. So we are able to draw a lower bound, which shows that a square root t regret is not avoidable. Since we are in the stochastic IID setting and we are not making an assumption on D, this is basically equivalent to the offline scenario where we want to prove that epsilon learnability of this problem needs 1 over epsilon square samples. Crucially, we cannot do better than that even in much simpler settings. Because, I mean, let's take the prototypical lower bound for offline learning, then if you want to understand, so let's say that we have a coin that can be epsilon biased to the tail or to the head with equal probability. So in order to understand the bias, so either it is biased on the tail or on the head, to understand that we do need 1 over epsilon square samples to do that with high probability. So this is a way of saying that in the simpler settings you can think of, apart from the trivial ones, there is no way you can do learning with less than those samples. As I told you at the beginning, we do have to impose some game theoretical constraints in the problem. Otherwise, we would need to be concerned with underbidding, overbidding, what are the actual players reporting to the mechanism, to the intermediary, and are the players participating in the game or not participating? I mean, we would have to assume very strong things without any theoretical grounding. So what we do here is impose game theoretical constraints in the problem, in the optimization procedure, in order to enforce these nice properties that, for example, truthful reporting and the fact that the players are actually participating in the game. So specifically, we want to enforce dominant study incentive compatibility and ex-post inhibitor rationality. So as I hinted at, dominant study incentive compatibility means that the dominant strategy for both the players is being truthful. So they do report their actual valuation to the intermediary. And also we want individual rationality, which basically means that given truthfulness, we want that the utilities are positive. If we did not have that, then of course the agents could just decide not to play and they would benefit from that. Now, an old theorem from more than 40 years ago, I mean, an adaptation of that theorem tells us that in order for this to be true, we need that the allocation regions need to be closed under moving to the left and upwards. And also, we need that the pricing rules should be the eastward and the southward projection of the valuation vector inside the allocation region. So let's say that this is the valuation vector, then the rightward projection is this one, and the leftward projection and the downward projection is this one. So the x-coordinate of the rightward projection is the price we are actually paying the seller, while the y-coordinate of the downward projection is the price we're asking the buyer. Intuitively, the seller gets the most he can get, and the buyer pays the least he can pay. This is the underlying intuitive reasoning. Our goal is thus learning the profit maximizing mechanism that is both dominant study incentive compatible and individually rational. The technical challenges here are enormous, mainly the fact that profit is not regular, so it is not continuous, so it is clearly not Lipschitz, it is not convex. Also, the fact that we don't have uniform convergence, because having uniform convergence would imply some learning result. So just to be clear, what's uniform convergence is basically requiring that the expected supremum of the difference between sample averages and actual expectations goes to zero. And this cannot be happening unless we restrict the class of mechanisms, so the hypothesis class we are considering, in a very dynamic way. So if we are taking the supremum over all the mechanisms, then this will not be the case. And moreover, for similar reasons, we cannot rely on fixed discretizations. Because if you give me any fixed discretization, then I can find a distribution such that with the best mechanism in the fixed discretization, I'm always a constant amount away from the optimum. So specifically, the lack of uniform convergence is shown by this picture simply. So let's say that we are drawing uniformly from this segment. In this case, what we can do is simply, for any sample that you're giving me, I can puncture out all the points from the sample and obtain a valid mechanism. For this mechanism, the profit is null, but clearly if I were integrating with respect to all the measure of the sets that I'm not considering when puncturing out, then I do get something which is not null. So clearly, a construction like this shows that for any sample that you give me, I can find a mechanism such that you are not capturing the profit for that mechanism with those samples. The expected profit of that mechanism for those samples. Also, let's say that you're giving me a fixed grid, right? So let's tackle the first point in the technical challenges. So in this case, I can, for example, let's say that we are considering the uniform epsilon grid. I can just say, okay, you want to use an epsilon grid, okay, and then I'm just I'm just choosing a distribution that's basically this blue triangle, right? So the best choice for me would be to just output the same triangle, because this is a valid allocation region. Now, in this case, my only option would be to output either the first red square or the second red square together with the first red square. But with these only two options, I'm always a constant amount away from the profit I could get by outputting directly this triangle. So this means that, examples like this show that fixed discretizations are really not the right thing. So let's say our compromise is restricting ourselves, so regularizing with respect to using epsilon simple mechanisms. So a mechanism is epsilon simple if its boundary is made up of 1 over epsilon axis aligned segments. So you see here that this mechanism has a certain allocation region which is determined by this boundary, and I am approximating this boundary with the epsilon grid. Now, the lemma that follows is that the approximated mechanism has a profit that upper bounds the original one up to certain precision to epsilon. To prove this, I mean, it's really simple because if you are inside the allocation region, then you are smoothly increasing profit as epsilon goes down. While what happens when you are inside the region, which is part of the approximated allocation region, but not part of the original allocation region, then in that case, the original mechanism does not obtain any profit, and the approximated region obtains some. So this is why this inequality is not two-sided. So our algorithm for the stochastic setting is the following. We compute the best mechanism on the past samples, so our empirical maximizer. And we can do this in polynomial time because this is basically computing a shortest path on a graph which is dependent on the samples. This is very important. And also, we then regularize the output mechanism by making it epsilon simple. So why we do the second step? We do the second step because we need some countermeasure to overfitting, because if we would be just blindly trusting the empirical maximizer, this would be a really bad idea because we don't have uniform convergence. So indeed, just doing this without any particular additional analysis grants us the first regret just by union bounding over epsilon simple mechanisms that can be outputted on this dynamic graph. So just to give you an intuition about what we are doing here, so related to how to use a uniform convergence result to get a regret rate, let's take into consideration the simpler case where we are union bounding, so it's not the tight one. So with this, we are only able to obtain a t to the first regret, but improving on analysis, we are able to get the right. So the idea here is that we consider the epsilon simple mechanisms that are generated by the t-samples observed. What we mean is that we consider the mechanisms that are outputted on the graph that's generated by the samples that were observed. In this case, the amount of mechanisms that we have to consider is of this order, right? So it's dependent on both t and the approximation factor that we are using to simplify the empirical maximizer. Now, the union bound can be done either, so I mean, this result can be obtained either by straight up integrating everything concentration or with standard multi-arm bandits results. This gives us a uniform convergence rate which is of this order. So log t over epsilon t with the square root. What this gives us is immediately t to the first regret, because what we can do is simply saying, okay, the expectation of the optimum mechanism is simply equal by linearity of expectation to the expectation of its sample average. Then we can bound the sample average of the optimum profit with the sample average of the empirical maximizer by definition of the empirical maximizer. And then what we use is the approximation result from this lemma here, which tells us that if we approximate, what we lose is at most epsilon. So we use this result here, and then at this point, we can just use the uniform convergence bound to relate this sample average with the actual expectation of the outputted mechanism. Summing over t, we get the t to the first regret, because what we are doing here is just bounding the instantaneous regret, so the one at a specific time step. As I told you before, this is not optimal because we can do something better. We can prove a sample complexity bound for a suitable subfamily, which we can call M epsilon star. And this subfamily has a certain properties that make it nicer to work with for probabilistic chaining to work. Probabilistic chaining is an important technique that was introduced by Talagrand in order to get better uniform convergence rate. So what we gain is that by restricting the soup not over this class, so we take the soup not over the class M epsilon, but over the class M epsilon star, what we get is that the rate here becomes log t over t without the epsilon at the denominator. And this is crucial because this allows us to get a square root t regret. The important thing is that this class M epsilon star is both distribution and data dependent, because we need some particular properties in order for everything to work. The overall argument is that our output belongs with every probability to this subfamily, and every element in this subfamily with every probability satisfies the regularity we need for probabilistic chaining to work. So we don't have time to talk about chaining, but the idea is that if we were just union bounding, then we would be taking a union bound over all the mechanisms that can be obtained at a certain precision. So let's say that we have this geometric progression of precisions, and let's say that I directly take the union bound at precision 2 to the minus 2, we are taking the union bound with the precision 2 to the minus log t. In that case, we are basically doing the naive thing, right? So what if we focus on a sequence of approximations that eventually get to the target one? So if we take into consideration all the differences between the different approximations in the sequence, do we obtain something better? First of all, your another question would be, how do we use this progression of approximations? The idea is that we can take the profit at the final target approximation level and telescope it over all the approximation sequence. And then what we can do is combining this geometric increase in precision, which basically gives us a strong decrease in variance, with standard concentration inequalities. Combining these two ingredients gives us a stronger uniform convergence. Overall, to conclude, we have a non-parametric mechanism design problem that shows a surprising and tight square root t regret. We can achieve this with an adaptive discretization of the space, which already gives us a t to the first regret, and we improve on this non-tight regret by using probabilistic chaining. The future directions, several, for example, what happens in the smooth adversarial setting? So our lower bounds holds for the adversarial setting in the oblivious case without any smoothness added on top of it. So for example, let's say that the adversary cannot pick any specific deterministic sequence, but he can only draw from a smooth sequence from a smooth distribution at each time step. Then what happens in that case? And also, our algorithm, the one that we are using here, is definitely non-private, because if you change any single coordinate of any specific sample, you may end up changing the surface of the boundary of the allocation region. And this is clearly, this is clearly not robust to differential privacy attacks. So in order to improve on this, we may be adding some assumptions and turn this whole framework into a differentially private one. So I thank you for your attention, and if you have any questions, feel free to contact me either by email or in person in Sydney.